Okay, so now we have the last equation that we should satisfy. Now maybe our solution will not satisfy this whatever the constants are, or maybe for some values of some choices of those constants, it will be satisfied. Now, any question before we continue? Yes? Because in this classroom there are no charges, there are no currents. It's empty.
What exactly is omega?
Which omega? This omega.
Yes.
Well, we said that if you just look at this point, the magnetic field at an instant will be pointing in that direction with some magnitude. This magnitude will get smaller and smaller. It will be 0, then it will be pointing in the opposite direction. So it will just oscillate back and forth. So this oscillation has an angular frequency. That is omega. Now this was what we had. To test the Ampere's law, we again need to choose a surface to calculate the electric flux passing through that surface and calculate this loop integral at the edge of that surface. Well, the first attempt may be just to consider the same loop. What is the electric flux going through that loop? And if you consider the same loop over here, what will be the flux going through that loop? Well, 0, because the area vector is pointing in that direction. The electric field is perpendicular to that one, so there's no flux. So we have to choose some other loop. Now, since the electric field is pointing in the vertical direction, let us just choose this loop. Now, the electric field, this is just this loop, horizontal loop over here. Now, the electric field is pointing upward. What is the direction of the area vector for this loop? You see, it is such a rectangle. It's in the x direction. Its magnitude is, let's say, this is dy. This thickness is again dz. This is dy dz, pointing in the x direction. Now the electric field, this was our electric field. Let me just copy both the electric and magnetic fields. So the electric flux is just E dot dA. This is equal to E0 cosine kz minus omega t times dy dz. This is the electric flux passing through that area. And so the phi, its time derivative is E0 omega sine kz minus omega t dy dz. So now we have one side of the Ampere's law. We know what this d phi E by dt is. But now we need to calculate this integral b dot dl over that loop. Again, let's just give some names. This is A, B, C, and D corners. The integral of b dot dl will be equal to, from A to B, b dot dl, from B to C, b dot dl, from C to D, b dot dl, from D to A, b dot dl. Now, this is our rectangle. B is pointing in that direction. Now, from B to C, it is this side of this rectangle. What is B dot dl? 0. Because dl is pointing in that direction. This is the direction of B at this segment, at this small side over here. So from B to C, B dot dl is 0. And similarly, from D to A, B dot dl is 0. This is 0. This is 0. Now, we have a contribution from the side A to B. This is the A to B side. The magnetic field is pointing in the same direction. So their scalar, the magnetic field, moreover, since it only depends on Z, along this side, Z is constant, so magnetic field is constant. So B dot dl is just B of Z times dy. It is the total length of that side. B is constant from A to B. I just take it out. What remains is dl. The integral of dl is just the length of that side, which is dy. Now I have the contribution from C to D. Now from C to D, my loop is moving in that direction. Magnetic field is pointing in this direction. They are pointing in opposite directions. So there is a minus sign. And now the magnetic field is at the point Z plus dz. And this is equal to minus the derivative of the magnetic field with respect to Z times dz dy. Well, you see, the integral of the magnetic field gives me the derivative of the magnetic field. And the flux is proportional to the electric field, so I have the derivative of the electric field is proportional to the derivative of the magnetic field. That is why both of them are at a maximum or both of them are 0 at the same time. I know my proposed B. This is my proposal for B. I can just take the Z derivative, and it would just give me, this is equal to B0 sine kz minus omega t times dz dy. This is the integral of B dot dl. And now the last thing is in the derivative. Well, let's say the derivative of the cosine brings me a minus. There's another minus over here. So there's no minus. B0 times k. Because the derivative brings a minus k times sine. There's another minus, so it's k times sine. Now, the Ampere's law just tells me that this integral this should be equal to mu0 epsilon 0 times the derivative of the electric flux, which is this one. Sorry, this is dz. No, this is dy, sorry. Okay. And again, I have many cancellations. So what I end up having is B0 times K should be equal to mu0 epsilon 0 E0 times omega. This is the second condition that these coefficients should satisfy. Now let's see, we had the previous condition. But now this our new relation tells us that E0 over B0 should be equal to K over omega times 1 over mu 0 epsilon 0. This is from this relation. We have the ratio E0 over B0, and this was what we had obtained before. Both of these should be true. So omega over K should be equal to K over omega times 1 over mu 0 epsilon 0. But omega over K was nothing but V. So the velocity of this wave should be equal to 1 over the velocity times 1 over mu 0 epsilon 0. Or V squared should be equal to 1 over mu 0 epsilon 0. V is equal to square root of 1 over mu 0 epsilon 0. We know the value of mu 0. We had measured the value of epsilon 0. And in fact, you can just measure the value of mu 0 and the value of epsilon 0 from electrostatics and magnetostatics. Just put two currents, measure on a wire, measure the forces that they exert. Well, mu 0 is something that we define. We know its exact value. Epsilon 0 is something we measure. Just put two charges, calculate the force, and then you are done. The force is related with this epsilon 0. And just if you put in those numbers, you get V is
that why speed of light changes in here or in the vacuum?
because you are just changing these parameters, the dielectric constant. If you remember our discussions on the dielectrics, if you want to calculate the electric field in a dielectric, what we did was we just replaced this epsilon 0 by the dielectric constant times epsilon 0. But if you do that, then the velocity of light in that medium changes. So this is, by the way, this is one of the, let's say, the most important motivations for us to identify this light by an electromagnetic wave. They have the same velocity. To say at least one thing they have in common.
Physically speaking, what exactly is
K.
that?
What is wavelength? Physically speaking, what is wavelength? This length, right? K is 1 over that length, physically speaking. I mean, you know the relation between the period and the frequency? The relation between the period and frequency is exactly the same as the relation between lambda and K. One is in time, the other one is in position. No, we get mu 0 from our definition of mu 0. We measure epsilon 0, and we can also measure the speed of light. Well, most of the time what is actually done is we measure the speed of light, and from that information and from the known value of mu 0, we determine what epsilon 0 is. Well, what is 1 ampere? That is the main question. You can either define 1 ampere and then measure mu 0, or you can say that, okay, will be the value of mu 0 and then measure what is 1 ampere. You have to start with some definition of some scale. Yeah.
Yani epsilon 0 ortama göre değişebiliyor ama mu 0
Mu 0 also changes from medium to medium. but not much. I mean, the changes in mu0 are typically of the order of 1 part in 10,000.
Yani epsilon zeroyu buradan ölçtüğümüzde mu0'yu sabit kabul ediyoruz.
You see, these are the values in vacuum, in empty space. Mu0 has a fixed value in empty space. In a medium, it has a different value. But what we do is we define mu0 in empty space, we measure the speed of light in empty space, and then we determine the value of epsilon 0 in empty space.
Başka bir ortam için bakmamız gerekirse yine mu0'yu
Well, everything will be changing. You have to measure everything.
o zaman
Now let me ask you one question. Mu0 is a constant, epsilon 0 is a constant, so we obtain a constant speed of light. With respect to which reference frame? Well, that was the problem before the Einstein. The Maxwell's equations, we didn't, I mean, if you remember our discussions of the Maxwell's equations, we had seen some problems that the predictions seemed to be changing from reference frame to reference frame, so we cured those problems. If you remember the example of a conducting rod moving in a magnetic field. So we had to, from that observation, since it was changing from reference frame to reference frame, the velocity of the rod is different in different reference frames. We had to say that if the magnetic field lines are moving, they create an electric field. So we had this induced electric fields. And by trying to fix all these dependencies on the reference frames, we ended up having a speed. But with respect to which reference frame? The Maxwell laws are valid in every reference frame, not just a particular one. They are constructed to be valid in every reference frame. Now the problem is we have this velocity, but the velocities, at least until Einstein, we thought that all the velocities depended on the reference frame. But it turns out that this velocity is the same in every reference frame, not just one.
To understand that, what course should we take?
In modern physics, you will study this in 202. Modern physics 202, next year.
So there is a reason why its speed of light is the same throughout any reference frame, right?
Well, do you call this a reason? If you believe in Maxwell's theory, Maxwell's equations, then it's unavoidable. But then why are the Maxwell's equations correct? Why do we have Maxwell's equations?
Well, we haven't been able to combine theories anyways, right? Like quantum mechanics theories and special theory of relativity, we haven't been able to combine.
We have been able to combine them.
We have?
Yeah, sure.
But we don't have a unified theory.
Now, we have a combined theory of Maxwell's equation with quantum mechanics. Dirac did that already in the 20s and 30s. That's quite an old theory. What we couldn't combine was general theory of relativity and quantum mechanics. That is what is still missing. But we have a quantum theory of electromagnetism. Now, any questions on this one? Yes.
How can we make connections with? We have.
Well, that is kind of the nice thing. I mean, you see, these mu0 and epsilon 0, they are constants in statics, not even moving reference frames, moving rods. And we relate it to something that is kind of doesn't even depend on charges. I mean, we are not discussing about charges. We are looking in a region of space where there are no charges. This is not the speed of the rod. I mean, you see, as you say, I mean, we started from by just simple observations. And that was one of the observations we had. If we have a moving rod in one reference frame, that is before adding this induced electric fields, in one reference frame there's an EMF, in the other reference frame there was no EMF. So we had to fix it somehow. Our theory didn't seem to be consistent with at least the Galilean relativity principle. The predictions seemed to be dependent on the reference frame, so we had to cure it. And we had to cure several other things. We had to add this displacement current, but then we had a theory at the end which predicts the electromagnetic waves moving at constant speeds in every reference frame. So that's kind of the miracle of physics. This is the result. This is the prediction. We started from simple observations and reached this important conclusion that there should exist electromagnetic waves that exist without the need of any charges, and they should be moving with such a speed in every reference frame. That is our prediction, which is basically based on simple observations. The next thing is, can we verify it experimentally? Do they exist? How do we create them? Well, one example is the light, but how are we really creating these electromagnetic waves? How are we creating light in these lamps? Okay, we just turn on the switch and the light comes, but how does it work? Why, when we heat something, it starts to glow? How is heat related with electromagnetic waves? And those are the things that we should discuss. Well, those we will be doing, the creation of these electromagnetic waves we will be doing tomorrow. But let's look at something else. Now, we had already seen that if there is an electric field in a region, then that electric field stores an energy. Do you remember the energy density stored in an electric field? This one? And there was also the energy stored in the magnetic field. So there are these energy stored in the electric field and the magnetic field. Well, let's see. We have these Here we have our electric and magnetic fields. What is the total energy density? Which is the energy density stored in the electric field plus the energy density stored in the magnetic field. This will be equal to 1 over 2 epsilon 0 E0 squared plus 1 over 2 mu 0 B0 squared times cosine squared kz minus omega t. But let's see. This is equal to V, E0 over B0, which is 1 over square root of mu 0 epsilon 0. Or E0 is equal to, let me just use the symbol C times B0. C is the speed of light. So the total energy is just 1 over 2 epsilon 0 C squared B0 squared plus 1 over 2 mu 0 B0 squared times cosine squared kz minus omega t. But remember, C squared is 1 over epsilon 0 mu 0 or epsilon 0 times c squared is nothing but 1 over mu 0. So both of those terms are equal. Here, epsilon 0 c squared is equal to 1 over mu 0.
So when there's the solution, do they convert from one to another?
Well, not really. I mean, you see, they are both maximum at a given point, and they are 0 at the same point, at the same time. At a given point, they go maximum, minimum, maximum, minimum, at the same time. So at a given point, you have a maximum energy stored, and then you have 0 energy stored in that region. What happens to that energy? Energy is moving. You see, we had these electric field lines pointing in that direction, let's say, at a given instant at this point, and magnetic field lines in that direction. And we said that with time, these electric and magnetic field lines, they're just moving. But so is the energy density with them. The energy density, the energy stored in this wave is actually moving. It's moving from one point to the other point. You are transferring energy using these electromagnetic waves. This is 1 over mu 0 times b squared, because they are equal. Let's say this is equal to 1 over mu 0 times c times b times b divided by c. I just put some weird constants. But c times b is equal to E0. Or c times B0 is equal to E0. This is what determines their magnitude. So c times b is, in magnitude, is equal to the electric field. And also keep in mind, here I had this cosine squareds, and these were just constants. Here b is not the constant. B is B0 cosine kz minus omega t. So that here, this cosine is now in this B. But the electric field and the magnetic field, they all have the same cosine. Because the electric field is nothing but c times b. Do you agree? I just knew I had figured out, found the relation between E0 and B0. I just put it in the definition of the energy densities. And I saw that the energy stored at a given energy density of the electric field at a given point at a given time is equal to the magnetic energy density at the same point. So these two are equal. Because c squared is equal to 1 over epsilon 0 mu. Because of this relation, the energy densities stored in the electric and magnetic field, they're always equal. And then I could write it in this form, but I also know that electric field is just c times b. So this is the total energy density. Now what I would like to do is I will just write this as cross b. What's the magnitude of E cross B? The product of the magnitudes times the angle between, sine of the angle between the two. What is the angle between the electric and magnetic fields? 90 degrees. Sine of 90 is just 1. So this, the magnitude of this product is equal to this one. This is the total energy density. Now let us look at this figure. Energy density of the electric field plus the magnetic field. No, these are densities. They are at a point.
Toplam enerjiyi sadece manyetik alana bağlı olarak yazabiliriz.
Yes,
Ama sadece elektrik alana bağlı olarak
correct.
elde edemeyiz. Yani bunun bir
No, we can. I mean, you see, what we know is electric field, we have that relation over there. If you just write in this equation B is equal to E over C, then we have an expression in terms of the electric field. But my point is trying to obtain this relationship, which will kind of makes it obvious that if electric and magnetic field, if any one of them is zero, this quantity is zero. And if I would write it in this form, it would just look as if, even if there is a zero electric field, in that case, I might be obtaining some energy density because of the magnetic field, but that is not the case. If you have an electromagnetic wave, if B is non-zero, E should be non-zero. If B is zero, E should be zero. So in this expression, it's more explicit, let's say. Both of them you should have both the electric and magnetic fields to be able to write this relationship. What is the direction of E cross B? It's in the direction in which the wave is moving. E cross B is parallel to the K vector, the propagation direction. Now let's see. This wave, we had obtained that, okay, if you just put, this is your total energy density, it just changes with cosine squared kz. So if you would plot it as a function of z, it just has such a behavior. So there are regions where there's a large energy density, there are regions where there's a small energy density, a large energy density, small energy density, etc. And this whole thing is moving with the speed of light. All of them are moving with the speed of light in the plus z direction, in the k direction. Now, if you would just consider such an area, I can just put an area over here. Just imagine this area. There is this chain of energy packets. Each one of these packets is carrying energy in forms of electromagnetic waves. So they are all moving with the speed of light in that direction. Then I can talk about how much energy passes through unit area per unit time. And that would be, well, this is the energy density, and it is moving with the speed c in the direction k. This is the energy, let's say, energy current. It's not the electric current, it's the energy current. Current density. Now, how we define, if you remember how we define the electric current density, we just imagine a surface area, we just counted how much charge passes through it per unit time, per unit area. That is how we had defined the electric charge current density. electric current density. Now we do the same thing over here, but not for the charges, but for the energy. So we have this area, we measure how much energy passes through this area per unit time, divide it by the area, and then we obtain the energy current density. So energy is flowing, that is what we call a current in general. Anything that flows is basically a current. So this is the energy current. It's not the charge current, it's the energy current, and its density, which is equal to 1 over mu 0 C E cross B times C in the direction K. So C's cancel. We obtain 1 over mu 0. But E cross B is already in the K direction. So it's just, here I take E cross B, which is a vector, take its magnitude, multiply by the unit vector in the direction, in its same direction, but that is that vector anyway. E cross B. This is usually defined as S. This is not the surface vector, this is the pointing vector. It is a measure of the energy flow, pointing. NTI, this is why NTING. It's just a name. It measures the flow of energy. Yes. You are not pointing at something. It's the name of the scientist. No. What will not exist?
Light exists because of the magnetic and the electric stored in there.
Yes.
Exactly. So it means that if I have two light, two photons interacting in a way, they can cancel out each other.
No.
The energy is stored.
They cannot cancel.
Why?
That we can discuss after the lecture. But they cannot cancel. You cannot come up with a configuration in which they will cancel. That's the problem. Now, what is momentum? Okay, mass times velocity. That is how we define the momentum of massive objects. So an object, if it doesn't have any velocity, it doesn't have any momentum. But an object also has an energy. So if an object has a momentum, it has an energy, we can say that we can imagine a point object having a momentum, but that point object has energy. You can say it's the mass energy or it's the kinetic energy, whatever energy you want to call it. But that energy is just moving. So if an object has a momentum, then the energy of that object is moving. So in that sense, you can also identify the momentum as the energy current. Now, for this electromagnetic wave, we cannot use the definition of momentum as mass times the velocity. The velocity is constant mass. I mean, there's no mass over here. But we can still use the concept of the transfer of energy. It's this pointing vector, where the momentum density of this plane wave this is equal to S over C. Why is it S over C? How do we know that this is the momentum density, etc.? That I will leave for your third year. Because the magnetic field line is everywhere. These magnetic field, electromagnetic wave is everywhere. I mean, if you create an electromagnetic wave that is localized in a finite volume, like this mass, then you can talk about the total momentum of that electromagnetic wave within that volume. I can just give you such a plausibility argument that it has to be 1 over C over there. You see the mass, you know the relation E is equal to mc squared. If I know the energy, there's the energy density. We had already calculated it. So from that energy density, I can just identify some effective mass over here. Well, if I identify that effective mass, then that effective mass is already moving at the speed of light, so the momentum will be just mc, which is E over C. This is the momentum. This is what we define by 1 over C. Now, of course, the effective mass for a plane wave is infinite because it has an infinite energy, but you can just convert it to momentum density, then here you have the energy density. So that's why we have this 1 over C over here. But this basically solves our initial problem. Although we didn't yet discuss how we create these electromagnetic waves, these objects are moving. But if they are moving, we have point objects. They create an electric field. Plus they are moving. If they are moving, there's also a magnetic field over there. So the electromagnetic field in this region already has its own momentum. It's not just these point charges that have a momentum, but the electromagnetic field in this space also has its momentum. If we want to talk about momentum conservation, we have to talk about the conservation of the total momentum, both that these point charges have plus the one that our electromagnetic wave has. And you can actually show in 2 years that sum is still conserved. The momentum of these two charges separately is not conserved because some of their momentum is transferred into the electromagnetic field in that region. It won't be a simple plane wave as we had discussed. It will have a more complicated expression, but nevertheless, since there is an electric field, there is a magnetic field in that region, there is a momentum in that region also, which is changing in time as the objects are moving. So the sum of all the momenta is still conserved. So that kind of resolves the initial problem that we had proposed. But of course, there is still one more problem we have. How do we create these electromagnetic waves? Yes.
Enerji density grafiği yapıyoruz. Grafiğin minimum olduğu noktalar hem elektrik alan içindekilerin hem de manyetik alanların sıfır.
True. The electric and magnetic fields at these points are zero.
Şöyle bir frekansa denk gelemezler mi? Yani biri maksimumken diğeri minimum.
No.
Birlikte maksimuma çıkıp birlikte minimum.
Yes. I mean, you can actually show that, in 2 years, you will show that they have to be maximum at the same point, minimum at the same point. What about? Light. Look for waveguides. You can guide waves. Fiber optic cables. They are basically guiding an electromagnetic wave of the visible spectrum. They don't have to be guided, but you can guide them. What? Nothing. You see, the charges also don't need to be stored. I mean, you can just take a bunch of electrons over here and throw it in one direction. That creates a current. It's not stored in anywhere. It's a current, still a current. I mean, the currents, they don't need to flow through conductors. That is the easiest current we can create. But still the problem, I mean, is there a medium that carries this electromagnetic wave, just like the waves in the ocean or in the sea? I mean, for years, people wanted to invent some medium. And they invented the concept of ether. I mean, when they realized that the Maxwell's equations predicts a fixed velocity, the first question they also asked, with respect to which reference frame? And they said, okay, it's with respect to the reference frame of the medium. What is the medium? Ether. What is ether? Nobody knew.
Isn't it like magic? Like generally, ether or something, elixir, magic, stuff like that.
Yeah, probably it's derived from that one. But nevertheless, that was the name given to it. And people started to look for it. In fact, Michelson-Morley experiment, the one that proved that the speed of light is the same in every reference frame, was an experiment looking for effects of ether. And then after that experiment, we know that even if ether exists, there is no possible observation.
Didn't they know back in that time speed of light changes in water or air?
Of course, but in vacuum, I mean, you can have reference frames in vacuum, different reference frames in vacuum. But in all those reference frames, the speed of light seems to be the same. But some people said that, okay, no, they are not the same in every reference frame. The speed of light has that value only in the reference frame in which the ether is at rest. It's the speed relative to ether. That was what they wanted to show. Anyway, of course it was hypothesized. And then in the experiments, they couldn't verify it. So we had to give up that concept of the ether. Okay, I will be giving a break now. If you have questions, we can just continue discussing outside. Also, your question.